Have you ever read a health study and just kind of scratched your head, wondering why a new drug or a diet seems to work wonders for some people, but does absolutely nothing for others? Well, the answer often comes down to this really powerful and often overlooked concept in health research. So let's dive in and break it down.
All right, here's our game plan. We're going to start with that mystery, that puzzling effect. Then we'll officially meet our main concept, effect modification. After that, we'll figure out how to tell it apart from its tricky cousin, confounding. We'll see how scientists actually spot it in their data. And finally, we'll wrap up with why this whole thing really matters in the real world.
So yeah, let's kick things off with that big puzzle. It's a question doctors and patients are dealing with every single day. You've got a treatment that's supposed to work, but when you look at the results, they are all over the place.
Let's put it another way. Think about something that's a known risk factor for a disease. What if its impact isn't set in stone? What if its power to cause harm, or not, completely changes just because some other factor is in the picture? That is the central mystery we're here to solve. And that, right there, brings us to our key term for the day. This whole phenomenon where things change each other's effects, it's called interaction. And it's not random. It's a fundamental principle of epidemiology.
Now, just so you know, if you're reading the scientific papers, interaction often goes by another name, effect modification. They're basically two sides of the same coin, so let's properly introduce the star of our show.
Okay, so here's the textbook definition. Interaction is when one factor literally changes the strength or even the direction of another factor's effect. The key idea here is that they don't just add up independently. No, they actually get in there and mess with each other's impact. For an interaction to even happen, you need at least 3 players on the field. You've got your main risk factor, we'll call it factor A. You've got the outcome you care about, the result or disease, let's call that Y. And then you have the secret ingredient, factor Z, the potential effect modifier. It's the presence of Z that can change the entire relationship between A and Y. And what's really fascinating is that this can go 2 totally different ways. If factor Z makes factor A's effect stronger, we call that a synergistic or positive interaction. But if factor Z actually weakens or maybe even completely cancels out factor A's effect, that's called an antagonistic or negative interaction. All right, pay close attention here because this part is super important. There's this other concept in epidemiology called confounding, and it gets confused with interaction all the time. But trust me, they are completely different things, and telling them apart is absolutely critical.
And for researchers, this is a non-negotiable point. You have to be able to tell these two apart. And why? Well, because one is a real discovery you want to study, and the other is basically just a statistical error you need to get rid of.
I think this analogy makes it super clear. Think of interaction as a team-up. The two factors are genuinely working together or maybe against each other, creating a real biological effect. Confounding, on the other hand, is a mix-up. It's like a statistical illusion. It's a third wheel that's connected to both your risk factor and your outcome, and it creates a false link that isn't really there. So that brings us to the bottom line for any scientist doing this work. Confounding is a bias. It's an error. You have to get rid of it to see what's really going on. But interaction is what's really going on. It's the discovery. It's the thing you want to tell the world about. Okay, so if interaction is this real thing that we actually want to find, how in the world do scientists spot it hiding in all that data? Let's take a look at how they play detective. So, the science gives us 2 main strategies. The first is to basically check if the effect of one thing is different depending on what group you're in. The second is a little more mathematical. You see if the combined effect of 2 things is bigger or smaller than you'd expect. For our explainer, we're going to zoom in on that first method, because it's a really intuitive way to get it. It's called heterogeneity of effects, and heterogeneity is just a fancy science word for different. Are the effects different in different groups?
Check out this super simple example. Let's say we're looking at the risk of getting outcome Y if you have exposure A, but we've split our people into 2 groups. Now get this. In the group where modifier Z is present, the risk from A is 20%. But look what happens when Z is absent. That same risk plummets all the way down to just 5%.
You see, the effect of A is not the same. It's not homogeneous across these 2 groups. That massive difference, that 20% versus 5%, that is the signal. It's the statistical fingerprint that tells a researcher, hey, there's probably an interaction happening here. Okay, so we've defined interaction, we've distinguished it from confounding, and we've even seen how to spot it. But so what? Why should any of us care? Well, this is where we connect all that theory to why it's so important in our actual lives.
At its very core, the whole point of studying interaction is to get away from simplistic, one-size-fits-all medicine and public health. Remember that question we started with, why a drug works for one person but not another? Well, this is how we answer it. This is the science behind personalization. And the real-world impact is huge. It lets us target health campaigns only to the people who will actually benefit. It is the absolute foundation of personalized medicine, designing a treatment just for you. It helps us write really specific safety warnings like, don't take this drug if you have this gene, which is a classic example of an interaction at play. Ultimately, interaction forces us to level up our thinking. It makes us realize that asking a simple question like, does X cause Y, just isn't good enough. The much better, much more powerful question is the one you see right here. For whom does X cause Y? So, I'll leave you with this thought. The next time you see a headline about a new medical study or a public health alert, think about this concept. Think beyond that simple headline and ask yourself, what are the hidden interactions, the secret effect modifiers that could be shaping health outcomes for you and for everyone all around you?